In this video, we'll learn about Ampere's law, which is kind of like the Gauss's law of magnetism. Think back to Gauss's law. In Gauss's law, we learned that the integral of E dot dA is equal to the Q that's enclosed by a Gaussian surface over epsilon naught. We learned this law after we learned a more general form of finding the electric field caused by a charged object, in which we looked at the electric field caused by a little piece of that charged object, dE, then added up all of the little electric fields by taking the integral. When we learned Gauss's law, we found that it couldn't be used in every situation, but when there was symmetry involved, it made our derivation of the electric field much easier than the first way we learned. Ampere's law is kind of the same. We're going to be using Ampere's law to find the total magnetic field caused by multiple currents, kind of like you see with these 4 circles on the left-hand side of the screen here. I have 4 wires, 2 that are carrying a current into the screen, and 2 that are carrying a current out of the screen. If I wanted to find the magnetic field at a point here, I'll label P. I know that I could find the magnetic field from each of these 4 wires and then add up those vectors. However, doing that wouldn't be the easiest thing in the world. So instead, we're going to rely on this law to help make our lives a bit easier. Ampere's law, as is written on your equation sheet, says that the integral of B dot dL is equal to mu naught times I. And while it doesn't say this on your equation sheet, this I in this equation is really the I enclosed or inside of something that we call an Amperian loop. So let's take a look at a quick example of an Amperian loop. Here's 3 wires that we see, I1, I2, and I3. And we're trying to find the magnetic field at some point. We'll say that that point is right here. So what we've done is draw an Amperian loop, or really just a closed loop. That's the reason for the circle and the integral symbol, showing that it's a closed loop that we make surrounding our currents. And B dot dL, dL would be the same as this ds that we see in this diagram. In other words, it's a vector that points in the direction that we're traveling around our Amperian loop. It will either be clockwise or counterclockwise. So B dot dL gives us is equal to mu naught times the current, the total current that's enclosed by this Amperian loop. We'll always choose a direction that we integrate around our loop, either clockwise or counterclockwise. And that'll affect whether we consider a current to be positive or negative. Similar to Gauss's law, we really can only use Ampere's law when there are some symmetry considerations. We'll look at 2 examples in this video of using it with a long straight wire, looking for the magnetic field both outside and inside this long straight wire. To understand a bit more about how to apply this law, we're going to think back to Gauss's law a bit. Our first step with Gauss's law was to come up to kind of define a Gaussian surface. That was often a sphere or a cylinder. Our first step here is going to be to choose our Amperian loop, the loop of that surrounds our wires, surrounds our current, and once again, we'll be relying on symmetry for that. And then we'll evaluate that dot product, and just like in Gauss's law, the dot product will typically start off by saying B dL cosine theta, and that's equal to mu naught times I. And then quite often, we're going to work with symmetry so that this cosine of theta will become 1. And hopefully, thanks to symmetry, the magnetic field will be constant. So we'll really just be taking the integral of dl, pull that magnetic field out. And typically that integral of dl will give us b times whatever the length is of our loop equals mu naught I. And again, we'll look at a couple examples of using that. There is kind of an important rule when it comes to those currents as you're adding up the currents, because again, this I is the total I that's enclosed by your loop. The general rule is that if you, using your right-hand rule, if you curl your fingers the way that you are traveling around your Amperian loop, then your thumb points the direction of a positive current. Let's take a look at this diagram up here again. So my Amperian loop would be going counterclockwise in this case. So if I'm using my right hand, I'd be looking at my hand as if my thumb is pointing at me. My fingers are curling counterclockwise. I1 is pointing in that same direction as my thumb, so it would be considered to be the positive current, whereas I2 is pointing opposite that direction, so it would be a negative current. So when I would be finding that I enclosed, I'd be doing I1 minus I2. Let's see how we can apply this law to find the magnetic field outside of a long straight wire. In this example, this long straight wire, we're looking at a cross-section of it. You'll see that current is a dot, which means that it's coming out of the screen toward us. There's already an Amperian loop drawn here for us. And if you think of what we already know about the magnetic field of a long straight wire, we know it depends on how far away you are from that wire. So having a circular loop is convenient here because every point on that wire would be the same distance away, which means magnetic field is going to be constant for that Amperian loop. We'll start out with the general equation for Ampere's law, which again is that the surface integral, or closed loop integral really, of B dot dl is equal to mu naught times I. And again, remember that that mu naught is that same constant that we've had before, 4 pi times 10 to the negative 7th Tesla meters per ampere. So I'll work with the left-hand side of my equation here, starting off by getting rid of the dot product by expressing this as the magnitude of that dot product. B dl cosine theta, and that's equal to mu naught times I. Thanks to this diagram, which was so kindly given to us, we can see that ES, which again, remember, that's the same thing as DL, it happens to be pointing in the exact same direction as my magnetic field. How convenient. That means that the angle between them is 0, so that the cosine of 0 degrees is 1. So now I'm left just with the integral of B dl. As I mentioned already, the magnetic field has the same magnitude everywhere on my Amperian loop, meaning that it's constant, so I can pull it out of the integral. And finally, I can evaluate this expression that's the integral of dl. If I think of the length of this Amperian loop, it would simply be the circumference of a circle. 2 pi times little r equals mu naught times I. This time the total in current is enclosed here. Just leave it as I. So my final expression says that the magnetic field is mu naught times I over 2 pi r, where r is how far away your point is from the wire, from the center of the wire. That was definitely a much easier derivation than when we did it using the Biot-Savart law, saying that dB equals mu naught over 4 pi times I dl cross r over r squared. So just like when using Gauss's law, as long as we have symmetry, Ampere's law is typically the easier derivation to go through. Let's look at using Ampere's law one more time. But this time we're going to look at the magnetic field inside of a long straight wire instead of outside of it. We're going to start off the exact same way, just by writing out our expression, the integral of B dot dl equals mu naught times I. And again, just so we remember, I'm going to put this as I enclosed. So we remember that that's the current that is inside of our Amperian loop. Once again, we're going to realize that thanks to symmetry, we're dealing with a constant current here. So current is the same everywhere in this wire, which means our Amperian loop, we're going to keep the same symmetry of the wire. So it's a circular Amperian loop. And if you kind of reasoned through it a bit, you could probably realize that that magnetic field would be in the same direction, or would kind of move in a circle inside the wire as well. So we start off by saying B dl cosine theta equals mu naught times I enclosed. And then we have the cosine theta being equal to 1 because the magnetic field is parallel to our dl vector, as you can see in the diagram here. And magnetic field, again, thanks to symmetry, because our Amperian loop is always the same distance from all parts of the wire, we can argue that by symmetry that magnetic field would be constant around that loop. So I can pull that out of my integral symbol. So I'm left with B times the length of that Amperian loop, which once again is the circumference of a circle, 2 pi times little r. Notice little r was the radius of my Amperian loop, and big R here is the radius of the wire. So basically, I get the exact same thing that I did with outside the loop, but there is a difference here, because that I that's enclosed is not the total current of my wire. That means we're going to have to come up with an expression for that current that's enclosed by my Amperian loop. Now, I mentioned to you we're going to assume that the current is constant everywhere in this loop, and we're looking at a cross section. That means that the current is the same everywhere in this cross section. And so if that's the case, we could say that the current density would be the same. In other words, the current that's enclosed by our Amperian loop divided by the area that's enclosed by our Amperian loop must be equal to the total current divided by the total area of our wire. And again, this area is cross-sectional. So I can find an expression for the current that's enclosed by multiplying the total current divided by the area of the total wire. And since it's a circle, we use pi r squared. And I'll use a capital R there since that's the radius of the wire, times the area enclosed by our Amperian loop, which would be pi times little r squared. So these two pi's cancel out, and I'm left with the fact that the current enclosed is equal to the total current times little r squared divided by big R squared. When I plug that into my expression for magnetic field, I have mu naught times the total current times little r squared divided by 2 pi little r times big R squared. And of course, this square cancels out with that r right here. And so my final expression for magnetic field is mu naught I times the radius of my Amperian loop divided by 2 pi times the radius of the wire squared. If you look at this expression, as little r approaches big R, this expression approaches our expression that we had for the magnetic field outside of a wire, which is good. That means it's a continuous function here. In class, we'll practice applying Ampere's law with numbers and calculating the magnetic field of some long straight wires, both inside and outside of the wire.